Hey folks, let's talk about electronegativity and bond polarity. Let's begin with defining electronegativity. Electronegativity is the attraction an atom has for electrons in a bond. It is unique to a bonding situation, so you do have to have bonds in order to really have electronegativity have meaning. If you stop and think for a second about the periodic table, and you think about all of the elements on it, and if you recall, we talked about the fact that different elements have different sizes of those atoms. And that as you go down any column on the periodic table, the elements get larger because you have more shells of electrons being added. But then as you go horizontally, the atoms get smaller because the larger nuclear charge pulls on the electrons in that shell and causes them to become or to get pulled closer to the nucleus. So if this is kind of the general pattern we see on the periodic table, and then we start and think about making bonds with these atoms. When two atoms come together, they kind of, they're gonna find that magic bond length where they have the maximum attraction for electrons. Think about what's happening to those electrons. They're attracted in a covalent bond to the nucleus of the other atom. The closer they are to that other nucleus, the greater that attraction is going to be. As a result, we see that the smaller atoms on the periodic table have higher electronegativity. So as we look on every vertical column, electronegativity gets larger as you move towards the top. And then as we look horizontally for our periods, it's going to get larger as you move left to right. It looks exactly like the trend for ionization energy. But it's going to tell us what happens when you form these covalent bonds. How attracted are the electrons in the bond for that particular atom? And that's going to have a huge impact on the way the bonds are going to behave and then ultimately on the way your molecule is going to behave. So let's take a look at that. The difference in electronegativity between two bonded atoms determines what we call the polarity of the bond. So I have down here on the bottom, I have the periodic table, and this is from ptable.com. This is just an image. And it has the different electronegativities on it. You can see the color coding. The more orange it is, the more electronegative those atoms are. And if you look at it, you can see values for the electronegativity. So in this particular version, they're written down here at the bottom. So fluorine has the largest electronegativity with a value of 3.98, where francium down here has a value for its electronegativity of only 0.7. And these are relative to one another. So this is a Linus-Pauling scale. It doesn't actually have units that we typically talk about. So these are my electronegativity values. If you think about forming a bond between two atoms, if they're both equally attracted to, or if electrons in the bond are equally attracted to both of those atoms or nearly equally attracted, you're going to have a very even sharing of the electrons. And that's what we call a non-polar covalent bond. And this happens for any time you have two of the same element being attached to one another, like an F2 molecule. Even though they're very electronegative, the difference in their electronegativity is going to be 0. Or it happens when you have two elements that have very similar electronegativities combining. So let's say I had something like carbon and sulfur. Carbon has an electronegativity of 2.55, sulfur is 2.58. Those are very similar in their attraction for the electrons. The electrons will be shared equally. That holds up to about 0.4. Right around 0.4, you start having a large enough difference in electronegativity that the sharing of electrons is no longer equal. We have at this point what we call a polar covalent bond, which results in unequal sharing of the electrons. Examples of elements that would form a polar covalent bond would be something like carbon and oxygen. Their difference in electronegativity is close to 0.9. And so the oxygen is going to be pulling more strongly on those electrons, and as a result, you end up with the electron density spending more time near the oxygen, and it's not an even sharing. If the difference in electronegativity is even larger, you end up with no longer sharing your electrons. You actually end up with a transfer of electrons. Do you recognize it? It's an ionic bond. The cutoff for that is a little fuzzy. We usually put it up close to 2.0, but I'm going to say ish up here because it does depend on the type of the elements that are involved and exactly what their electronic structure looks like. An example of elements that would form an ionic bond would be something like oxygen and sodium. The difference in electronegativity here is 2.51. And so the oxygen is much more electronegative and will actually take the electrons away from the sodium, forming an anion and leaving behind a sodium cation. Now, bond polarity can be represented with arrows and with partial positive and negative symbols. Let's take a look at an example. So if I have a nitrogen and fluorine bond, so here's my nitrogen bonded to my fluorine. I can check and tell that the difference in electronegativity, so take the big number minus the little number, is going to be 3.98 minus 3.04. That's 0.94. That is a polar covalent bond. So it's polar covalent, and the fluorine is going to be more attracted to those electrons, or the electrons are more attracted to the fluorine. So we can show that by drawing an arrow above the bond that shows the electrons being pulled toward the fluorine. And we put a little plus on the tail end of the arrow to remind us that the other side of that bond is going to be partially positive because I pulled some of the electron density away. So this side is going to be partially positive, and we can represent that with a little partial positive symbol. It looks like a little swoopy thing. That's the Greek lowercase letter delta. And then the fluorine side of the bond is going to be partially negative. So there's two ways to represent bond polarity. Take a look at one more. Let's take chlorine and carbon. Here again, if I look at my electronegativities, carbon is 2.55, chlorine is 3.16. So I have a difference of electronegativity of about 0.6. This time though, the chlorine's the more electronegative one. So I would show that by drawing an arrow pointing towards the chlorine, because that's the direction the electrons are going to be pulled. And that leaves the chlorine with a partial negative charge and the carbon with a partial positive charge. Again, these are polar bonds. We don't need to draw these arrows. They are officially called dipole moment arrows for things that are non-polar.